In the last video, we developed an intuitive sense of what force was. And one of the things we recognized was that it changed the motion of objects. We also took a look at the different kinds of forces that are out there. Here we're going to focus more on how forces change the motion of objects, and in so doing we will come up with a more rigorous definition of force. And the usual codification of the laws of motion, they're called, is due to Isaac Newton, which again was developed while he was hanging out at the family farm, avoiding the Black Death when pandemic swept Europe. Although the ideas aren't entirely his own, they build on ideas that had been put together by other workers for the preceding 80 years, but those ideas were in a more embryonic form. They weren't completely stated. They had some technical issues. Newton was the one who was able to take all those ideas, distill out what was the correct, distill out the correct essence of all of these different ideas and codify it into the three laws of motion. Now, I will spare you presenting them to you in Latin. I mean, he wrote in Latin because that was the more or less universal language of scholarship back in the day. Just like in physics now, the universal language of scholarship is pretty much English. So I'll spare you quoting them in Latin, but I will quote them to you from Newton himself. This is because most statements of Newton's laws of motion attempt to make the prose easier to read, and that's generally laudable. Newton definitely was of the sort where his writing style was why use 5 words when 39 would do just as well. But in this particular case, I find his statements to be the most precise, and I find they generate the fewest problems. So with that, I will go with the first of the 3 big ideas that he came up with. Newton's first law of motion, also known as the law of inertia. So quoting from Newton in English translation, every body perseveres in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed thereon. Okay, so that was a mouthful. So what does that all mean? What this does is it puts together 3 ideas. One of the big ideas is the idea of inertia. So inertia is the physics world's name for the property that all objects have, that it is their natural state of affairs to move in a constant velocity. So this constant velocity could include 0. That's the state of rest part of the statement. Or it could be anything, 17 meters per second north, whatever. And what Newton is saying here, and I find this statement amazingly non-intuitive, but it is correct. It is the natural state of affairs for an object to move at a constant velocity forever. Now, we know that in practice, we haven't really seen objects do that. So what causes a change from this natural state of affairs? That would be a force. And so actually this statement also operationally defines force. A force is that interaction which changes the velocity of an object. So that's our more rigorous definition of force. So what we're saying here is if you saw some soccer ball whizzing past you at 20 meters per second heading east, the natural state of affairs for it would be to continue to do that forever. In fact, in such a straight line that it would fly off tangent to our spherical Earth and fly off into space going at 50 meters per second, 20 meters per second forever. Now, why doesn't it do that? Well, one, the force of Earth's gravity it turns out, is causing the object to fall toward the Earth. So instead of flying tangent off the surface of the Earth in a straight line forever, our soccer ball will curve back toward the surface of the Earth. What else is changing its velocity? Well, a soccer ball is not a small object. And so when it moves through the air, you really cannot neglect how hard the air is pushing on the ball. And that will actually have a pretty substantial influence on the trajectory of the ball. One thing that's a little less obvious, and you have to dig down into some of Newton's discussion of it to even start to tease it out, is he also defines the idea of an inertial observer. So this is an observer who can do physics. In other words, they can do physics calculations and have them be consistent. And some other observer could also do them and be consistent. And although those observers might disagree with each other, they know how to translate to each other. It turns out that in Newton's framework, and this does eventually many centuries later get challenged by D'Alembert, and then Einstein riffs off of D'Alembert's ideas. But in Newton's framework, which is a perfectly fine framework here, he says that to do calculations in his framework, as an observer, you have to be moving at a constant velocity. And so let me just give a quick example of how that sort of thing works. So let's say that I am riding on a skateboard at a constant velocity. Like so. And I toss a ball. Now you, standing over by the side here, would realize that the ball has some initial horizontal velocity, and then I give it some vertical velocity as well. And having studied ballistics for a bit now, you would say that the trajectory that the ball takes is a parabola. I would look at it, though, and say that the ball is going straight up and down. And you would say that I would say that because my horizontal velocity is the same as the ball. So every time I measure it, the x-coordinate of the ball remains unchanged. So I only see a change in the y-coordinate of the ball. So I would say the ball goes straight up and down. You would say it goes in a parabola. But it turns out it's okay. Both of us can be inertial observers. And as an inertial observer, you are allowed to say that you are stationary and the whole rest of the universe is moving around you. So we've already explained it from your perspective. You see a parabola, and then you understand that I would see it as going straight up and down because my x-component velocity and the ball's x-component velocity are the same. From my perspective, as an inertial observer, I would be allowed to say that I am stationary. And you say, wait a minute, but you're on a skateboard. I said, well, that's fine. The whole earth is sliding out from underneath my skateboard. And I tossed my ball straight up and down. But I would say that you would be moving to the left. So every time you measure the x-coordinate of the ball, it increases. So although I know that I threw the ball straight up and down, I would predict that you would observe a parabola. And so then you might ask, who's right? And the answer is we both are. And that's what Newton is getting at here. We're both right. We can both do a physics calculation, get an answer, and we can both predict what the other person would measure for it. Now, I'm not going to make a super duper huge deal with this. There will be one spot where when we get into what are called elastic collisions, where this observation will actually be really handy. But that's really about the only spot this inertial observer thing is going to matter for this treatment. It will come up a lot in later courses when you study Einstein's theory of special relativity. But anyway, the big take home here is Newton's first law of motion. States the concept of inertia, that's the natural state of affairs for an object to move at a constant velocity forever. And it also defines a force as that interaction which causes an object to deviate from exhibiting its inertial motion. Okay. This cues us up for Newton's second law of motion. So that one says, the alteration of momentum is ever proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. Okay, so he's using very geometric language here. And so I'm going to go ahead and write the statement the way we would write it in mathematical symbols now. And then I'm going to have to pause for a bit on it and go to a simpler case. So what he is writing is that if there are unbalanced forces acting on objects such that the net force is not zero, a quantity called the momentum, whose symbol is a lowercase p, will change. Now, we haven't defined this yet. Give me a few more video series to get to that point. But this turns out to be the correct statement of Newton's second law. However, there is an approximate form And this approximate form is a correct form in 99 and 44/100% of all cases you will ever care about. And that is to say that an object's acceleration will be equal to the net force applied on it divided by the object's mass. Now, this statement is only true with two constraints. The first constraint is that the mass is a constant. And most of the time, that's okay. There are two notorious examples where the mass of an object will change throughout its motion, where we would have to use this version of Newton's second law rather than this simplified version. The first case is if we have, say, something like a raindrop falling down through the sky. As the raindrop falls down, it will glom on additional water molecules onto it, and its mass will increase. The other notorious example is launching a rocket. It turns out that roughly 90% of the mass of a rocket is its fuel. And because of operational differences in rocket motor design, when it's operating where there is an atmosphere versus where it's not an atmosphere, where there's not an atmosphere, it usually makes sense to design what are called staged rockets, where the first stage uses rockets that are optimized to work in an atmosphere, and the second stage is optimized to use a rocket motor that works outside of an atmosphere. And so, in addition to burning all this fuel at a ridiculous rate, you also just plain literally throw away the first stage of the rocket, and then the mass of what's left decreases substantially. So, all that to say that when you're launching a rocket, its mass is changing all the time, and it's changing rapidly. And again, you would have to use the first version of Newton's second law, and you would have to use the methods of calculus to obtain Solovsky's first and second rocket equations. That's beyond the scope of this treatment, but again, the big caveat here is the mass of the system has to remain a constant to use this A equals F net over M form. The second of these is that we require that the motion be non-relativistic. So this means that the speed of all the objects involved is substantially less. So, remember, less than just means a lot less than. So the speed of an object has to be substantially less than the speed of light. Well, that's not usually a big deal. Even the electrons in a hydrogen atom move at pretty much non-relativistic speeds. About the only thing in practical life that ever moved relativistically that you would encounter would be, say, if you can still find a old style color TV set that actually has a tube. It turns out that the electrons that get fired at the screen to cause the screen to light up had to move at relativistic speeds, and so the engineers designing those actually had to take relativity into account in order to make sure that the picture looked good. But otherwise, pretty much nothing in our everyday life moves at relativistic speeds. Speed of light is just a shade under 3 times 10 to the 8 meters per second, so 300 million meters per second. That is awfully fast. And again, here, this is because that when objects are moving at relativistic speeds, it turns out that we have to more fussily define momentum. And it turns out that in that more fussy definition of momentum, you have to use F net equals delta P over delta T. And it will not reduce to this simpler form. So these are the two big constraints, is that the mass is a constant and the objects are moving slow compared to light, which means that basically as long as you're not like launching a particle in a high energy particle accelerator or something like that, you're good to go. All right, so we should figure out what the units of force are. So we can take a look and say F would be, so this, I need meters per second squared here. And I would be dividing by kilograms to be left with meters per second squared. So the force, unit of force has to be kilograms times meters per second squared. This combination occurs so much it gets its own special symbol and name. We call this the Newton in honor of Isaac Newton. And it is 1 kilogram meter per second squared. The equivalent unit in the English system is the pound. And a pound is 1/32 of a slug foot per second squared, where a slug is the unit of mass in the English system. Okay, so let's just try a couple of examples here. So first off, let's just start by pushing on a box. And we'll assume no friction or anything like that. So just plain, here you are. There's your hand. You're pushing on a box. Let's say you are applying a force of 10 newtons. Let's also say the box has a mass of 2 kilograms. By Newton's second law, since A equals F net over m, and masses are always positive, the acceleration of an object will always point in the same direction as the net force. Here we're only positing this one force. Maybe you're pushing on this in space or something. So we can conclude already that the acceleration will point in the same direction as the force, and we just want to know how big it is. Okay. So we can just go ahead and work in components, work in magnitudes here, since we've already got the direction worked out, and say that A is F net over m without the arrows, because they're both pointing in the same direction. We already worked that out. There's only one force, so it's F over m. So it'll be 10 newtons over 2 kilograms. So a newton is a kilogram meter per second squared over 2 kilograms. Cancel, cancel. And we're left with 5 meters per second squared. All right, that's cool. Now let's take a look at a little more complicated example. And I want to use this to show how you can start to integrate ideas and also use the problem-solving technique that I call thinking backwards. So again, let's say, I don't know, you're in space or something, so we don't have to worry about any other forces. Let's just say you're pushing on a crate with a force of 5 newtons. We'll say the crate has a mass of 2 kilograms. We'll say that the crate starts at rest. I push on the crate for 2 seconds. And what I want to know is how fast is it going at the end, V final. and I want to know how far it traveled. So again, we can do our usual trick of defining this to be x initial equals 0. So this is really asking for x final. All right, so we've identified our situation using our STAR model of situation, tools, answer, review. And now what I want to do is show how it is that physicists often think about a problem and how often you should be reading a solution of a problem. So if you're looking at a solution of a worked problem in a book or something like that, or even when I'm doing them, a lot of times it may look like the starting point just came out of some nether regions that you really don't want to think about too hard. But the reality is that the reasoning went backwards of the presentation. So let me show what I mean by that. So when I look at a problem like this, let's say, okay, we're asking for V, we have V initial, we're asking for V final, we're asking for X final, we're given a delta T. Hey, this has kinematics written all over this. And so then you start to write down, and so you're when you look at this, you're thinking about what was the last bit you did to get the answer? Well, the last bit you did to get the answer was you did some kinematics. So you realize the last step of this has to be do kinematics because we see all this kinematics-y stuff. We're given delta t equals 2 seconds. We're asked for x final and v final. So that sure seems like kinematics, but now here's the issue. We're given delta t. We're asked to find both x final and v final. And that can be okay as long as we have the acceleration. Oh crap, I don't have the acceleration. How am I going to get the acceleration? So then the big thought is I need to somehow get the acceleration. So this is the, and then you say, well, okay, now how can I buy myself the acceleration? You realize, oh, hey, yeah, I can do Newton's second law of motion. I need to know the acceleration, but I've been given the force. It's 10, what was the force? 5 newtons, sorry. It's given that the force is 5 newtons, and it's given the mass was 2 kilograms. So yeah, I'm good to go there. I can find the acceleration. So this is the think backwards stage of things. So the last step, do kinematics. You find that you needed something to do that. So then you go back a step in the process and figure out what you would have had to do that. If this were a more complicated problem, you might then say, oh crap, but in order to get that, I need this. And then you go back one more and so forth. But then the thing is when you write up the solution, you start from this bottom bit because you need this acceleration, then you go forward. So when you look at a lot of worked solutions, if you're trying to understand where they got it from, go to the bottom of the solution. Look at what they're doing. And then you can realize, okay, they realized that the end process was do this, and then they had to figure out how to get themselves this input that is where they're starting the problem with. All right, so now that we've got that, we can go ahead and in our answer part, now that we've got our tools identified, we can actually start to execute. So Newton's second law says that the acceleration is equal to F net over m. And here we'll take the x components of that. The acceleration points entirely along x, and the only force that we're thinking about is the force of that push, F over m. So now we're solving forwards. So think backwards, but solve forwards. Now we're free to start doing kinematics. So we can say, all right, I need to know my V final. I'll use missing x. I actually have a choice. Well, so, yeah. Well, since I don't know x yet, using missing x is probably the way to go. So this one's going to say V final equals V initial plus AT. V initial 0, so we can set that to 0. And then we can take my expression for the acceleration and substitute it in. So we get that V final is F over m times, whoops, that should be delta t there, delta t. So this will be 5 newtons over 2 kilograms times 2 seconds. A newton, remember, is a kilogram meter per second squared. So cancel, 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 cancel. Yay, I'm left with meters per second. I have 5 meters per second. All right. Now to solve for my x final, I have a wealth of information because now that I've solved for V final, there's actually nothing missing. So this is a wonderful situation to be in. When nothing's missing, what you can do is you can look at any of the 3 equations that have an x final in it and pick the one that you think is the easiest to solve. So I look at the key equations of kinematics, and I decided that for me, and you might make a different choice, but for me, the one I find the easiest to solve here would be the missing A. That's the one that says x final equals x initial plus 1/2 V initial plus V final delta t. X initial is 0, V initial is 0. So this will be 1/2 times 5 meters per second times 2 seconds. Cancel, cancel. 5 meters. Awesome. All right, so we were checking our units all the way along as we were doing our review, but let's just observe that we did that. And are the answers plausible? Yeah, 5 meters per second is a reasonable speed, and moving something 5 meters sure seems plausible. Cool. Alrighty. So in the next video, I will take a little bit of time to explore a bit of a subtlety about mass. Catch you in the next one.